So more the number of alpha hydrogen, and you have seen. Hello everyone, welcome back to Plutus STEM. So today we are going to discuss a very important effect, that is hyperconjugation. So we have already covered up various other effects such as mesomeric effect, inductive effect, electromeric effect. So all these effects, they play a very important role in this the various concept of chemistry, like dealing with to knowing the stability of a carbocation, stability of alkene, and how this reaction is going to proceed or not. So the various other factors that are being affected by these important effects. So we have already covered various other effects. So today we are going to discuss a very important effect, that is hyperconjugation effect. So this effect is also being known as Baker-Nathan effect, and it is quite similar to resonance effect, but here we are going to see in the resonance the bond pi bond and sigma bond. There was a conjugated pi bond and sigma bond, delocalization of pi bond we have seen over here, and in this case we are going to see the delocalization of sigma electron. So that's why it is quite similar, just, and that's why the name is termed as no bond resonance. So this is a no bond resonance effect. So we are going to see why this is being termed as no bond resonance instead of the resonance effect. So what is the difference between the resonance and this hyperconjugation effect? So yeah, so this is, now we are going to see what is going to happen over here. The basic thing is that if we are having delocalization of sigma electron, very simple definition of this is going to be delocalization of sigma electron. So we are going to see over here delocalization of sigma electron. So where this delocalization is going to see that this delocalization will be generally of CH bond. Generally we are going to see the CH sigma bond is going to be delocalized with the help of its neighbor sp2 hybridized. The delocalization of the CH sigma bond, that is sp3 hybridized with an sp2 hybridized carbon. So how this whole phenomena is going to take place, we are going to see. Let's take an example of a carbocation. If we are having a compound like this, this is the compound which we are having over here. This is a carbocation and it is a sp2 hybridized. It is a sp2 hybridized. So I have told you the delocalization of sigma electron to the neighboring, or you can say alpha position, with respect to the alpha position. So now this is like our sp2 hybridized carbon, and these two are alpha position. With respect to this, these two are alpha position. So this, if you see how this delocalization can take place, this is having a positive charge. To get this positive charge stabilized, what this carbon 1, and let's say this is carbon 2, it is asking its hydrogen to donate 1 electron to this carbon because it is having deficiency of electron, and we are going to get a result like this: CS3, CS2, C positive, sorry, double bond H positive. So if you visualized over here that this bond, the both the electron of this bond, they are coming at this carbon and it is forming a pi bond, and this negative charge, positive charge of this carbon is being stabilized over here, and this hydrogen, it is losing its electron pair, electron bond pair. So this bond pair, that's why this there is no bond over here. There is no bond present over here. That's why this is being termed as a no bond resonance. That's why it is being termed as no bond resonance. So when this hydrogen loses its electron pair, so it thinks that I need to get it back. So what is going to happen now? This carbon will ask another hydrogen attached to itself to donate its lone pair. Again, what will happen? This phenomena will come back. It will come back and it will again become like this. And this time, what will happen? This hydrogen, this time this hydrogen, now this is going to donate its electron pair like this, and it will become like this. So understand it better, these bonds are like this. So in this way, each and all the alpha hydrogen present can do this sigma bond delocalization. The same way I have shown you for this hydrogen, this hydrogen, this hydrogen, and these two hydrogen. All these hydrogen can show this delocalization. So if you see for this hydrogen present at 2, it will come like this and it will become like this. Hydrogen. So this is the way how this stabilization of this positive charge is being taken place over here. So this carbocation is stabilized by the alpha hydrogen present to its adjacent position or the alpha position. So this is the same reason why we are seeing that 3-degree carbocation, they are more stable than 2-degree carbocation, 1-degree carbocation, and the methyl. So if you see the reason over here, this is a 3-degree carbocation, and if you see at alpha position, these are 3 alpha position, and we are having 9 alpha hydrogen, and these 9 alpha hydrogen, they are going to stabilize this carbocation. So this is going to be more stable as compared to secondary. In the secondary, there are 2 alpha position and 6 alpha hydrogen. 2 alpha carbon and 6 alpha hydrogen. And for this 3 alpha hydrogen present at alpha carbon. And in the last, for methyl, zero alpha hydrogen. So more the number of alpha hydrogen, and you have seen that how these alpha hydrogen, they are stabilizing this carbocation. So that's why we have seen the many examples that 3-degree are more stable than 2-degree and then 1-degree. The main reason behind that is this whole hyperconjugation phenomena. So I hope this is being clear, and this phenomena is not only restricted to this carbocation. This can also be shown for the free radical. CH3 CH2. This free radical is being present, and generally we know that free radical is also sp2 hybridized, and with respect to this sp2 hybridized, the alpha carbon is this one. So over here 3 hydrogen are present. Over here we are having 3 hydrogen. So what will happen over here? This bond break like this. And these two free radicals, they combine with each other and make a bond. Clear? So like this we are having this bond. So the same phenomena can be repeated with different hydrogen. The same hydrogen can also show this. This one, and the third hydrogen can also show this phenomena like this, and we are going to get a free radical. So you can see this free radical is being stabilized with these 3 alpha hydrogen. So you can see that these alpha hydrogen, they are also stabilizing this free radical in the same way like I have explained you for this carbocation. The same reason we can see over here that these free radical, they are also being stabilized by this hyperconjugation phenomena, and 3 degree is more stable than 2 degree than 1 degree for the free radical also. The reason is quite same over here also, this hyperconjugation. And another system where we are going to generally see this mechanism, that is alkene. That is alkene. So if we are seeing an alkene over here, this is our alkene, and if in this alkene, if you see, these two are sp2 hybridized carbon. This is the alpha position and sp3 carbon. The necessary condition for hyperconjugation is the nearby carbon to the sp2 hybridized carbon must have the must be sp3 hybridized and must have the alpha hydrogen. So the condition is being fulfilled over here. So now what is going to happen? This can come over here and it can become like this. The same phenomena can be repeated with this different alpha hydrogen. So there are 3 alpha hydrogen are there. So 3 different phenomena we can see over here. So this can also break down lower one. So this is the way how this alkene, they are showing this conjugation effect. For this double bond, they are moving down like this, and this conjugation, we know the conjugation leads to the stability, and over here we are having a similar type of conjugation effect, that is hyperconjugation, the sigma and pi bond delocalization. and it is also stabilizing this alkene. This is also stabilizing this alkene, and here we are having 3 alpha hydrogen. So if you compare the stability of the alkene, so we can see over here, if we are having this alkene, number 1, number 2, and number 3, and number 4. And if we see the stability of 1, 2, 3, 4, if we compare the stability of 1, 2, 3, 4, so over here we are having 3, 6, 9, 12, 12 alpha hydrogen, or you can say 12 hyperconjugation possible. Over here 6 alpha hydrogen, over here 3 alpha hydrogen, 0 alpha hydrogen. So more the alpha hydrogen, more will be the stability of alkene. So that's why we can say 1 is more stable than 2, than 3, than 4. So on the basis of this presence of more number of alpha hydrogen, we can also determine the stability of these alkenes. So we have seen the 3 system in which generally these hyperconjugation formula is being shown. So one was the carbocation, another was the free radical, and third was the alkene. One more type of phenomena, sometime it is being shown over here. If we are having a group like this is a benzene trichloro group are being attached with this benzene. So what we are going to see over here, this Cl, this is, you can say, a Cl are there, so they are electron withdrawing due to the inductive effect. But if we want to know that, so whether the upcoming group is coming at ortho and para position, so we cannot tell this through this inductive effect, because inductive effect is working on this more at this position and lesser at this position, because inductive effect is a distance phenomena. So on the basis of inductive effect, we cannot tell that there is a ortho-para-directing or a meta-directing group. But this hyperconjugation phenomena, help us in determining the this meta effect, meta secreted effect of this. It is a meta directing. Why? How? Because this comes over here, and this Cl leaves like this. A positive charge at ortho position. So this can be further move like this. A positive charge at para position, and in the similar way, again the same concept we will see, and the electron will move at this time at this moves like this. Okay, sorry. Over here, and in this case we have moved the electron from here to here. So this sorry, here I have shown this movement a bit wrong. This is like this, and after that after the movement of electron, the final product will be so we can see that positive charge is present at ortho and para position. So that's why any nucleophile which is going to come, that will prefer the meta position. Electrophile will prefer the meta position because more number of electron are comparatively electron pair are more at this meta position as compared to ortho and para position. So this we can see this effect, hyperconjugation effect as the meta directing nature of this compound. So this is the various concept which we have seen from this hyperconjugation. So in short, we can say that delocalization of sigma electron with the neighboring sp3 delocalization of sigma sp3 hybridized carbon, delocalization of hydrogen of sp3 hybridized carbon with the sp2 hybridized carbon. It can be alkene, it can be carbocation, and it can be free radical. So various concepts I have shown you in quite details, and the next upcoming video we will be discussing some other related concept to this general organic chemistry. Thank you.